Hello everyone, I'm Abhishek and today I'm going to represent my project Kernel Scheduler. And the reason behind Kernel Scheduler is kernel multi-core load balancer. So let us first understand what is the problem. Let us say there is a scientist who want to divide or distribute his tasks across multiple cores. And a very good example would be, let's say you are having 4 core, 8 core, 64 cores. Across those cores, loads are coming in and all of those loads are getting targeted into a single core. So that is very much problematic in terms that you are losing out your computational efficiency. You are not using your computational powers. Rest of your XYZ amount of cores are sitting idle. Only one core is getting used at a time. It is very same as of a problem you can describe in a restaurant where one chef is getting multiple orders and rest of the chefs are sitting idle. Why? Because there is no load balancing aside those. So to tackle these kind of problems, as these problems are much there inside the Windows 11 also, and even in Linux, they are not aware of the particular facts of the problem that we will talk into later in this video. So let us say, what is the main problem that our Chrono scheduling system solves? Basically, the Chrono scheduling system solves around, let's say, IO processing, input output, CPU utilization, kernel aware, and cache intensive operation. It even understands about your layer 3 cache operations and multiple internal load balancing and low level queries also. It is aware of these kind of facts which the Windows native processor is unable and is generic about those. So let us dive into this project. I will show you a very good example of how we are doing this, and in the later on sections I will also tell you how it does. Let us start by injecting 100 loads. Basically we are using right now the work stealing algorithm. So it will try to steal the work from one core and another core and distribute across. As you can see, the load remains consistent and each of the cores are getting utilized. There is no core that is sitting idle, as is seen in the example right now what I have shown you. Now let us change the algorithm to least loaded and inject 100 tasks. Again 100 tasks. As you can see, the throughput is nearly 500 tasks. Again, let us go for round robin and let us put down a 1000 tasks. This Q value represents total number of tasks remaining. A value is number of active cores inside this particular box. Each box is a core. There are 12 cores in my system, so it is showing 12 cores. These are specific details of my system like AMD Ryzen 5, AMD Radeon, and Lenovo, and Windows 11. Rest of the systems are in the dashboard. As you can change your algorithms from here. You can shut down the engine of this scheduling system, inject out tasks as many as you need, and this works on a push based migration and it has WebSocket inside it and very much more other details. So what is the main problem that it is trying to solve? How it is acting up? The Chrono OS is acting up like orchestra. Orchestra guides you how to solve the problem. It doesn't allow you to solve the problem by your own ideology. It will tell every code to perform in a harmony or a sync and doesn't necessary. So in the rest of the remaining section, I will let my teammates cover up how this dashboard is working, how the internal algorithms, hardware, load balancing, and core scheduling we have done. So let us dive in.
Hi, I am Alok. In this section, I will explain how Kronos actually sees your hardware and how it decides which core gets which task. Kernel Detection. Kronos start by asking Windows, who are you? What are you made of? We do this through three detection mechanisms. First, we read the CPU brand directly using the CPU instruction. That lets us ask the processor for its identity. We get things like Intel Core i7, AMD Ryzen 9, the exact brand model, and stepping. Second, we query get logical processor information to build a complete map of your system, how many logical cores you have, which logical cores share L3 cache, share the physical cores are cache hierarchy. Third, we check Windows registry and WMI to detect your GPU, your motherboard, available system RAM, and window version. Now, why does this matter? Because when we schedule tasks, We want to keep related tasks on course that share cache. If tasks uh, uh, if tasks are read data from memory, we want task B, which use that same data on a core sharing the L3 cache with task A. That's the performance value. And now three scheduling algorithms we used here. First, round robin. This is used because this is very predictable and simple and fair. And second algorithm is least loaded. This one is smarter. Before placing a task, we check which core has the fewest tasks waiting. Put the new task there. When a new task arrives, least loaded puts it on that core which has low task because it has capacity. There are also pros and cons of there. Pros is our balance current load, prevent boot Linux, and cons are does not react to overload quickly. And third algorithm we used work stealing. This is our most sophisticated algorithm. Imagine core 1 finished its task and now idle. Instead of waiting for new work, it steals a task from an overloaded core. And this also have a pros and cons. Pros are zero idle time and optimal utilization and handles variable workloads. Slightly more overhead but negligible. The queue structure. Each core has its own core queue. This is critical for performance. Each queue is protected by its own critical section lock. Why separated lock instead of one global lock? Because if all cores had to fight over a single log, that becomes your bottleneck, like having one security guard checking 8 doors with 4 independent security guards. You get a much better throughput. The monitor thread run continuously, checking if any core is overloaded. Uh, if so, it productively pushes tasks to less loaded cores. We detect uh, So the recap: we detect hardware using CPU ID and WMI and registry queries. We map code topology and cache hierarchy. We offer three scheduling strategies: round robin for predictability, least loaded for intelligence, and work stealing for maximum efficiency. Each core has its own queue with its own lock to avoid contention. Next, my teammate Shubham will show you the dashboard, the real time visualization of all this happening live.
Hello everyone, I am Subham Kumar. So now you understand the scheduler, but how do you actually see what Kronos is doing? That's where the dashboard comes in. We embedded a complete HTTP server and a WebSocket server indirectly into Kronos. No external runtime, no Node.js, no Python. It's all native Win32, WinSock22. When you start Kronos, it launches a HTTP server on localhost 8080. You open your browser and boom, you get a real-time dashboard. The dashboard updates 20 times per second. Every 50 milliseconds, Kronos send fresh data via WebSocket. What does each metric mean? Utilization, percentage of a time that core is running task 0 to 100%. Queue depth, how many tasks are waiting on this score. Active task, currently execute task. Efficiency score, a variable based metric. The closer to 100%, the better balanced your load is across all cores. At the top of the panel, you see a system manifest. Why display this? Because Kronos detect all of it. This proves that the system understands your hardware completely. The dashboard is not just a monitor, it's a controller. You can first is the inject task. Click any button and click any task, and that many tasks get distributed across the course using the current scheduling algorithm. Each task perform uh, computation to stress test the scheduler. Second is the switch algorithm in real time. Click round robin and watch the dashboard instantly change how tasks are distributed. No downtime, no restart. The third is the monitor efficiency. As tasks run, you see per core utilization bar, efficiency score in real time, queue depth updating every 50 meter per second. It's like watching a conductor adjusting an orchestra in real time. Now, WebSocket communication. Here's the technical magic. How does the browser get updates 20 times per second without polling? Browser asks every 50 seconds. Any update? If nothing changed, there's network overhead. Our way of WebSocket browser connect once, then Chronos pushes data whenever it's ready. The server initiates the conversation, not the client. This is why our dashboards feel so responsive. There's no lag, no polling overhead. Behind the scene, the dashboard calls these REST APIs. Behind the scene, the dashboard calls these REST APIs: get API info, get API status, get API bench count, get API algo, get API stop. If you wanted to integrate Chronos into a large system, you could call this API programmatically, maybe a cluster manager, querying multiple Chronos instances, or an automated testing framework. So the dashboard is three things: a monitor, watch your system in real time at 20 Hz, a controller, inject task, switch algorithm on the fly, an API, integrate Chronos into large application. All of this, the HTTP server, WebSocket communication, the beautiful UI is embedded directly in a single C executable. No external dependency, no bloat, just pure performance. And there you have it. And there you have it, from Abhishek problem statement to Alok scheduling algorithm and hardware detection to our real-time dashboard. Chronos is a complete production grade kernel aware multi-core scheduler. We have built something that detects hardware at a kernel level in man, detect hardware at the kernel level, intelligently distributes tasks across cores, provides real-time visibility into performance, requires zero external dependency, is compliant with academic requirements, is suitable for real-world development. Thank you for watching. If you have any question, feel free to ask.